Continue. Perfect. Okay, guys, as always, interrupt me, ask lots of questions, make comments. I'll be happy to stop at any time. Previously, we started this big topic of concentration. Here is the logic of what's happening here, really. Normal distribution, Gaussian or normal distribution, Gaussian or normal distribution is very nice. As you know, the curve is beautiful. The density of it is so nice. Why is it nice? It's particularly nice in the useful way for statisticians because it concentrates tightly. Means that if G is normal, let's say it was mean 0 and variance 1, then it concentrates tightly around its mean, which is 0 in this case. And we proved something like this, e to the minus t squared over 2. So this is the mean, and we're asking what's the probability that the Gaussian random variable deviates too much from 0 by at least t. And that probability is small. It's not just small. It's not like 1 over t or 1 over t squared. It's super small. It's absolutely tiny. It's even smaller than exponential. It's even minus t squared. So, and that's what statisticians love because it gives them very good confidence intervals. If something is Gaussian, we know it with very, very high confidence that it will be near its mean. So that's one advantage of having Gaussian distribution. Okay. Then we ask, all right, how do we know things are Gaussian in the normal world, in the real world? We have a problem, and where does Gaussian arise? Gaussian distribution. How can we assume that something is normal? The answer is provided for us by the central limit theorem. So the central limit theorem says that sums of independent random variables are approximately normal. But, and the devil is always in the details, this approximate is too bad. This approximate is within about 1 over root n, the sum of n independent random variables. The approximation is about 1 over root n error. And that is too big in the usual circumstances. Well, we placed our hope in the Gaussian distribution. We said we should be so confident. It's like e to the minus t squared, very, very tiny probability usually. And this is invalidated basically by this error, which is too big. It's 1 over root n. It's not exponentially small. So, okay, so that's a problem, big problem. Because in fact, what you learn about the flips of coins and how confident are we that if you flip the coin n times, that the number of heads will be around n over 2. We build these confidence intervals based on the understanding that the things are approximately normal, and that's not true. They are approximately, but the approximation is too bad. So what do? We give up with a normal distribution. In fact, our new and ambitious goal is to just forget about normal, forget about central limit theorem, and just try to prove concentration directly for a sum of independent random variables without comparing it to normal distribution. So this will be a direct approach to concentration. One example of which we'll prove today, and this is called Hoeffding's inequality. And it basically says that what we're hoping for, tails like this, Gaussian tails like this, they're true for sums of independent random variables, but not because of the normal distribution, just directly. In this version of Hoeffding's inequality, we will, just to make it more dramatic, we will work with distributions that are as far from Gaussian as possible. Gaussian is very smooth and discrete. We'll work with the simplest discrete distribution. So the Gaussian is continuous. We'll work with discrete distribution, namely Bernoulli. And this is what we stated last class. Suppose we have independent and identically distributed symmetric Bernoulli random variables. And symmetric Bernoulli, remember Bernoulli random variables take 0 and 1 only. This time I will allow them to take two values -1 and 1 with equal probabilities. -1 and 1 with equal probabilities 1/2 each. And the reason it doesn't really matter. The problem is that with a normal Bernoulli, if I said 0 was probability 1/2 and 1 was probability 1/2, the mean is not 0, expectation is not 0, expectation is 1/2, so I have to subtract it. And the variance is not 1, I have to normalize it, and that's a little painful. It's just for aesthetic reasons, we prefer to work with symmetric Bernoulli, which we know the mean is 0, expectation is 0, and the variance is 1. Agreed? Yeah. So it's already normalized. Perfect. Okay, here we go. Then, so we build the sum of these random variables, just like that. We normalize it. And I divide by square root of n. Does anybody know why square root of n a natural normalization here? Normally you would normalize by 1 over n, just average, but why square root of n is a natural here? Hey, you know, I know somebody knows.
Square root of variance.
Oh, so what do you say? Square root of?
Variance.
Of the variance. Yes, Evgeny, exactly. Because square root of n is the variance of the sum. Sorry, not the variance. The variance of the sum is n. Agreed? The variance adds up. The variance of each term is 1. The variance of the sum is n. Now, the standard deviation, therefore, is the square root of that, square root of the variance, which is square root of n. Okay, so why do we normalize by square root of n? Is we want this sum to have variance 1, unit variance. So just to make this clear, this has mean 0 and variance 1. And why do we need that? Because I want to compare it with the normal distribution. Sorry, not I want to compare, but kind of in the back of our mind, we should have this normal distribution that has mean 0, variance 1. All right. So we look at this tail probability. Let's do one-sided tail first. Probability like this, greater than t. And surprisingly, we get Gaussian tail minus t squared over 2. So just like for the Gaussian, for the normal distribution that also had mean 0 and variance 1, we have the same result. And that's where we stopped last time, and then today we'll prove this theorem and then make applications of it. Any questions? Good. Okay, the argument, the proof is very important, very useful. Apart from this particular theorem, it's just a very useful tool. So you want to pay even more attention to the proof than to the result itself. The proof is by the MGF method that we will learn now. This is MGF stands for moment generating function. What is this Ukrainian term for it? In case you learned it, I'm not sure. Moment generating function.
Генератриса.
Oh, that's nice. Oh, that's nice. It's very, very beautiful term. Thank you. Okay, so here's how it goes. Remember Markov inequality. That's our first kind of basic approach. Markov inequality says that we can always bound this probability by the expected value divided by t. Okay, expectation of this divided by t. Why is it not what we want? It's not what we want because divided by t, that gives us just a linear rate, 1 over t. And we want much better rate. So Markov is not so good. Okay, now hold with me then. Next thing is Chebyshev's inequality. Chebyshev's inequality gives us a deviation, which is of the form sigma squared, the variance, divided by t squared. A little better than Markov. Markov was 1 over t. Chebyshev tail is 1 over t squared. So we're going in the right direction there. We just need to keep going, right? From Markov to Chebyshev and so on and so forth. Okay, still far, but better. Let's just ask ourselves, how did we ever get to Markov, from Markov to Chebyshev? Just lecture 6. How did we get to Chebyshev? We squared both sides. To get Chebyshev, we square both sides and then apply Markov. Yeah, okay. So that's how we got Chebyshev. Square both sides and apply Markov. And we get t squared, an improvement. Okay, now we want to have an exponential improvement. So instead of squaring both sides, what's our best deal here? We should exponentiate both sides. Got it? Okay, so same thing, only better. So we need to exponentiate both sides. And that's what we'll do. And to exponentiate, we need to choose the base. It's like we can do e to the t, but we could do like 2 to the t or 3 to the t or 4 to the t. We don't know which one is better. So we leave ourselves some room. We choose a parameter, the base, we choose lambda to be determined later, TBD to be determined. And then we multiply both sides of this inequality, of this interior inequality. Multiply both sides by lambda. In fact, I want square root n on the other side too. So by lambda square root n. And exponentiate both sides. So our probability, that's the blue probability, then becomes, okay, so we multiply by lambda root n, so we get lambda here is greater than, and here we get t lambda root n. Okay, so I just multiplied by a lambda root n and then exponentiate. So exponentiate like this, exponentiate like this. Nothing happened here, no math, it's just did this thing in preparation for Markov's inequality. And now we apply Markov. Markov's inequality, which, let's recall, Markov's inequality just says that this tail probability is bounded by the ratio by expected value of the random variable, and here the random variable is this big thing. And the denominator is this. It's the right-hand side. T lambda. Okay, shall I recall Markov? Z is greater than something is less than expected value of Z over that something. So we applied that. Perfect. Okay, so the denominator is just a fixed value, e to the minus t lambda root n. And the numerator, what do we do here? We exponentiate the sum. So it's e exponentiate the sum. That's a product of exponentials, right? It's factors. So we can write it as a product of exponentials, e to the lambda xi. Good. So far, so good. Again, so far, nothing really happened. We just rearranging the terms, applying Markov. Okay, now is a kind of a crucial step. Now we're claiming that I can swap to interchange the expected value and the product. I can bring the expected value inside. Why could we ever do that? When can we do this? When is it true that expected value of xy equals expected value of x times expected value of y?
When they're independent.
Exactly, when there is independence. So this is where we crucially use the independence property. So we use independence and bring the expected value inside. And we get the product of these things. Good. Okay, so now I'm claiming that all of these things are the same. All of these terms of the product, the factors here, they're all the same. Why? Yes, Pablo.
Identical distribution.
Exactly. All of the xi's have identical distribution. And we exponentiate, take expected value, it's a number, we get a number, and so this number is going to be the same. Since xi have identical distribution, the same distribution. Perfect. So we have the product of n terms that are the same. Let's just call it x. X is just one of them, I guess. To the power n. Oops. And what is x? Well, x is just like each of the xi, they're symmetric Bernoulli. X is distributed as a symmetric Bernoulli random variable. Okay, good. Now what? What is this called? This has a name, actually. E to the expected value of e to the lambda x. There's a name in mathematics for this object.
Characteristic function.
And that is almost the characteristic function. If I had I in front of this, the complex identity, that would be the characteristic function, right? And it is, yeah, characteristic functions is best known. Without the I, and I don't have the I here, this is called the generatrice, the moment generating function. It's a cousin of the characteristic function, so you're not far from. True, this is MGF of X. Good. Questions? We're good. Now notice that at this time, the complexity of the problem dropped down. Now we're not facing a very difficult situation. The difficult situation in the beginning is that we have a sum of independent random variables, very complicated distribution. Now we have just one symmetric Bernoulli. What can be easier than symmetric Bernoulli? Minus 1 and 1. It takes only two values. We should be able to figure this out. Let's figure it out separately. So let's compute the moment generating function of symmetric Bernoulli. It takes values 1 and minus 1 with probability 1/2 each. So how do you compute the expected value? It's you take the probability times the value plus probability times the value. And that is because, again, X has symmetric Bernoulli distribution. Is this computation clear? Yeah, that's how you compute expected value. So this is e to the lambda plus e to the minus lambda over 2. And this thing also has a name in mathematics. What is it? It's lesser known. It's one of the hyperbolic functions. It's called hyperbolic cosine. It's a hyperbolic cosine, and it looks like this.
Of lambda, you mean?
Of lambda, yes. Thank you. Yeah, hyperbolic cosine looks like this. It's e to the lambda, e to the minus lambda. It's like a parabola, but it was exponentially fast growth of the branches. Okay. All right, so this is that. And now let's see. So we have this hyperbolic cosine for each term, and then we raise it to the power n. So we'll have to deal with this to the power n in the next step. I could do it, I think, but it will be a big expansion, big binomial expansion. We would like to avoid it. So what we would like to do is to bound the hyperbolic cosine by something like e to the something something something. Then it would be easier to deal with this to the power n, right? And if you do the Taylor's expansion, I did it offline. If you do the Taylor expansion of this, the best you can bound it is with is e to the lambda square over 2. This happens for any lambda. Use Taylor's expansion to prove this. Do it yourself. It's a pretty good approximation near 0. E to the lambda square over 2. Okay. You can do it fine. Okay, look. So let's put it back into the probability, into this formula, this probability. So we have probabilities then bounded by this number is bounded by t lambda root n, and this is our moment generating function bound raised to the power n. Oh, perfect. Nothing can be better than this, because we can bring this into the common exponential function et lambda root n plus lambda square n over 2. Excellent. So far, so good. Okay, this is getting very nice. Now, as you can notice here, lambda root n feels like its own random variable. So if I call this mu, then this is mu squared. So let's just redefine. Let's just pass to this new variable mu. T mu plus mu squared over 2. Hey, perfect. This is a nice function. Okay, what do we do with it then? What's our goal? Again, our goal is to prove the bound like e to the minus t square over 2. So I would like to make this e to the t square over 2 here. All right, and there is mu standing in my way. There's mu that we didn't have in the beginning. What is mu? Mu is related to lambda, and what is lambda? And lambda was an arbitrary number. Like all what we argued about holds for arbitrary lambda. So this bound holds for arbitrary mu. What should we do now?
Minimize by mu.
Minimize, choose the best one, right? Mu is arbitrary. So we should choose the best one we like. Now minimize in mu. And yeah, and this is easy. This is a quadratic equation. So mu will be, I think, t, I think. Mu equals t. We get minus t squared plus t squared over 2, and we get e to the minus t squared over 2. Yay! Done. Got our Gaussian tail. Perfect. So this is our first results about concentration. A really, really nice method that can be applied generally, and then we will apply generally the MGF method. If we look at the beginning of this proof, it's not about symmetric Bernoulli distribution at all. Like all of this could be done for in complete generality. Only in the very end here did we use the symmetric Bernoulli, but the architecture of this method is very flexible. Any questions about the proof? Good. All right, here's our beautiful result that is called Hoeffding's inequality. That's what we just proved. And the result says that if we look at the sums in this particular case, if we look at the sums of symmetric Bernoullis, they behave like Gaussians. And as far as the tails are concerned, you can think that they're Gaussian basically, because the tail bounds are the same. So, for example, the corollary would be that in n flips of a fair coin, the probability of having at least 3/4, at least 75% of the heads is exponentially small. It's e to the minus, and we did this calculation, I believe it's e to the minus n over 8. I think we did this calculation last time based on the assumption that we can approximate by a Gaussian. And the assumption was wrong, as we know, central limit theorem didn't work, but now we reinstated it. We just entered through the back door here. So it's still the same thing. And one more example. If it's not symmetric Bernoulli, it should still work. In n flips of a biased coin, let's say a coin that comes up heads with probability less than 1/4, let's say. The probability of having at least half heads is also exponentially small. And I think I can't remember the constant, but it should be exponentially small still. So it's a nice exercise to do yourself, just to, instead of symmetric Bernoulli distribution that takes values with probability 1/2 each, make different probabilities and check that the method still works. So instead of 1/2 here and 1/2 here, make it maybe like 1/4 and 3/4. And things should still work. So that's a nice exercise to do. So again, the point here, the real point is that these probabilities are super, super tiny. So we're very, very confident. They're not just small. It's not just unlikely that you will see this big discrepancy between heads and tails, but it is exponentially unlikely. So unlikely that you'll not be able to see it in your lifetime, something like that. And that is given by Hoeffding's inequality. This is our first tool that we needed, a sharp tool that we would need in the high dimensional world soon. Questions? Good. Okay, now we got applications. So here's one application to the classical problem of statistics, estimation of the mean estimation. It's problem number one in statistics, right? You have, so here's a problem. We have a distribution with an unknown mean, and we would like to estimate it. Estimate the mean mu of a distribution of some distribution, and you estimate it from a sample. Let's say x1 through xn. That is drawn independently from this distribution. From the distribution. Yeah, statistics 101. So you have, we want to estimate the average salary in some city, and we draw a sample like 1,000, ask 1,000 people, what's your salary? And we would like to estimate the salary from that sample. Okay, what do we do classically? What's the usual solution? Average, right? Just take this 1,000 people, add their salaries, divide by 1,000, output, and go home. So the classical solution is to take the sample mean, which is denoted mu hat, which denote mu hat, will denote mu hat. So you add these salaries together and divide by capital N. And in statistics, the hat stands usually for the estimator, something that we derive from the sample and that's supposed to estimate the mean mu. Okay, so this is expected value is good, right? Expected value of that estimator, if we just by linearity, that's true. So this estimator is unbiased. Unbiased estimator, that's what we say in statistics. And the error, that's the more important thing now. The most important thing now is the error of this estimator. What do we do for the error? We just subtract it from the true mean, and then we take the square, take expectation. That's called the mean squared error. Mean squared error. Well, that's just a variance of mu hat, just by definition, it's a variance. And the variance, we know how to compute the variance of that thing. Variance of the sum is the sum of the variances. And that gives us sum of the variances. And we divide by n squared. That's because there is a square in the variance, so it's homogeneous with a power of 2. variance of each xi, let's say it has mean variance sigma. Sigma. So maybe we should add into the problem, we should say estimate the mean mu of a distribution from a sample, and the variance of the distribution is sigma squared. Okay. So sigma, and we have sigma divided by sigma squared over n. So the error, when we take the square root, the error is on average sigma divided by square root of n. On average. Okay. I bet you all know this, and we already discussed that the error, as the sample grows, the error goes down at this rate, the rate of 1 divided by root n. It's not great, but that's truth. That's what we have. And in fact, you can prove, and this is a much deeper result, that it's possible to prove that there is no estimator that beats this. We can say, well, maybe the classical solution is not good. Maybe we're not supposed to just sum this. Maybe we do something smarter and get smarter about this and get a better error. No, no matter what you do, no matter what the estimator you choose, that's the truth, and that follows from Rao theorem, but I'm not going there. If you take information theory, you'll see. So that's a truth. That's a ground truth. How confident are we about that truth? The confidence interval. We can do Chebyshev's inequality just to check, right? What's the probability that the error is not sigma over root n, but maybe t times larger? So I'll put t times sigma over root n. What's the probability to make 3 times that error? Well, Chebyshev's inequality says that you should take the variance here. The variance is sigma over root n. Sigma squared over n. That's the variance, and divide by the right-hand side. Squared, and I get 1 over t squared. That's how confident we are. So for example, if I ask, what's the probability that the error is 3 times higher than the average? Chebyshev's inequality says the probability of that thing is 1 over 9. Is that good? Not really. It's not so bad, but it's like 1/9. Can we do better? Can we improve the confidence? Let's make an ambitious goal to the Gaussian. Just like in the Gaussian situation, we would have e to the minus t squared over 2. But can we do it completely generally, in full generality? Just know mean and variance. Can we always, can we be that sure? Can we build maybe some other estimator that has a better confidence interval than this? What's your instinct about this?
X1.
Say it again.
X1.
X1. Sorry, I didn't catch that.
Estimate.
Should be, yeah. Should we be? Do you think it's possible to improve this generally? Just knowing the mean and the variance. Is it possible to get Gaussian tail like this? Okay. My first reaction was no, because if you only know the mean and the variance, then Chebyshev's inequality is your best bet. Right? You can't really beat Chebyshev inequality if you only think you know mean and variance. Maybe the tails are heavier than the Gaussian. How can you get the Gaussian tail out of nowhere and spin the goal out of hay? That's impossible. But surprisingly, and this is a very surprising result, that you can do this actually. Yes. Yeah, you can actually, just knowing the variance and just knowing that the variance is finite and the mean is finite and nothing else, we're not assuming Gaussian distribution of X or maybe bounded, nothing else, we can upgrade the confidence interval in the mean estimation to like this, as if Xi's were Gaussian themselves, which is very strange. Okay, so here's a theorem. And we will prove there exists an estimator mu hat. Mu hat is taken, mu tilde. This. It's not going to be the sample mean. Sample mean is bad. Something else. With a surprisingly tight confidence interval. T sigma root n, same thing. Smaller than twice e to the minus. Well, maybe I should tone it down a little bit. I'm not so sure about divide by 2, but some constant width is definitely true. Ct squared for any t. And c is just an absolute constant. I just can't recall what it is, like 1/3 or 1/4 or something like that. Okay, is the statement of the result clear? Yeah. Totally amazing. How I was looking at it. Well, I kind of know the proof, but it's every time I look, it's a miracle. How can you only assuming the variance get the Gaussian, the normal tail? What if your random variables have heavy tails? They're not even Gaussian or not even nice to start with, and you can improve this. Okay. So, but that's possible, and we'll do it today. So, the proof again. The proof maybe is more important than the result itself, and the proof is based on the estimator that's called the median of means estimator, MUM estimator. Hey, does anybody know? Does everybody know what median is? Median of a set of numbers. Right? I give you 10 numbers, and the median is the one that breaks it into 2 parts. Like half of the numbers are smaller, and half of the numbers are larger. Okay, so if I say, let's say that the median salary, let's say in the United States, I don't know what it is, like $30,000 a year. Median salary means that 50% of the population earns less than 30,000 and 50% earns more than 30,000. Okay. Perfect. Now, you guys tell me, why is median, what is better about median than mean?
It is robust to outliers.
Exactly. Median is robust to the outliers. That's true. So maybe if there is somebody like Bill Gates or Bezos who makes billions of dollars and the rest is small, then maybe that one salary of Bezos will drive the mean, the expected value, to some crazy amount. But the median will stay the same. It's just partitions, right? Equal half, equal half. So if one of the points goes away, the median stays there. So the median is more robust. And that is what we will use in this theorem. Okay, let's do it. So what's median of means? We partition the sample into, let's say, some blocks, let's say k blocks of size m each. Just need to make sure that m times k equals n. And then we take means of each block, and then we take medians. Okay, so it's like this: xm then the next block, and so on and so forth. This will be our block 1, block 2, so on and so forth, block capital K, and they are M elements in each block. So partition like this, take means first in each block. There's M elements, so I'm taking the means like this in each block, like that. Then we take medians, the median. Let's say mu tilde will be the median of these numbers. Median of means. Good. So we divide into blocks, take the means of the blocks. Now we have K numbers, and then take the median of this K numbers. Yeah. Good. Okay, that's a full disclosure. That's our estimator. And we're claiming that it's very good. It's better than just taking the mean of the fall of the entire sample.
So we split deterministically, basically just into equal pieces. We don't. This B1, B2, BK are not like random, or they're just sequential.
Yes, exactly. Good. Yeah, that's a good question to clarify. Yes, we split deterministically, going from 1 to the third and so on and so forth. We don't rearrange them. We don't pick them. We just whatever first, M people come to us, we take their mean, and then next M people, and so on and so forth. Yeah. In practice, it's actually sometimes useful to rearrange them first, just scramble them randomly first and then partition. So take the random things, because things may change over time, and so it's best to scramble the sample, but we're not even need to do that in this theoretical situation. So we take that, perfect. Let's check that this is actually a good estimator. Okay, first of all, let's look at the accuracy of each mean estimator. The accuracy of this mu j hat. It has, well, the mean is always correct. The expected value is always the same. They are all unbiased estimators, obviously. The variance equals, see, we just did this before. Let's see. Let me see here. The variance is sigma squared over n, but this time we're not taking n, we're taking m of them. So the variance is sigma squared over m. And this is the previous page. Okay, so we do Chebyshev's inequality to look at the, let's just do one-sided. Mu plus t sigma over root n, that's our target accuracy. And we do Chebyshev's inequality, and we get, let's see, so the variance here divided by the right-hand side squared. This is Chebyshev. Yeah. Okay. Remember Chebyshev? Maybe I should remind this. Chebyshev goes like this: probability is z minus its mean is greater than something is less than variance of z divided by something squared. And that's exactly what we did with, but we did one-sided inequality. That's all we need for now. Okay, let's simplify this thing. Sigma cancels, I believe, and goes on the top, t squared on the bottom, and m on the bottom. Okay. Now, n over m, that's k. That's a number of blocks. And in this case, so we get k over t squared. Okay, and let's just make it 1/4. I don't know. We don't care. Let's make the accuracy of each mean estimation pretty crude, 1/4. And for this, we set k to be t squared over 4. It's up to us how we split, right? It's median of means, but we have the freedom to choose how many blocks to do, and this is how many blocks I want, t squared over 4. But let's be it. Okay. So now something interesting happens. I have a pretty basic and bad estimation of the mean with confidence 1/4, but a lot of them. I have k of them, k independent estimates. Each of them is very low confidence, 1/4. But now what we can do is to make a vote of them. Think of them as voting procedure. All of these people are maybe unconfident about who they're voting for, but together, if they're collectively voting for something, that boosts their collective confidence. So here's how we make this happen. The ultimate estimator is the median of them. And the median is kind of a vote, 50 for, 50 against. Okay, the ultimate estimator is the median. Now, suppose this is a bad event, that the median, we overestimate the median, too large. The median is too large. So this means, okay, this is a median. The median, remember, the median is like 50% here and 50% here. So this is a median. And if the median is too large, then at least half of the estimators, at least half of them are too large. Are mu plus, larger than mu plus g sigma. Yeah, if I say that the median of the salary is larger than 30,000, that means that at least half of the people, at least 50% of the people earn more than 30,000. That's all I'm saying. And here's 2, right? If the median is too large, then at least half of them must be too large. That's the definition of the median. So this is because this is a median of mu j's. Perfect. Okay. So now we can think of coins. Each estimator is too large with probability 1/4, let's say, at most 1/4. So it's like it flips a coin. Each estimator is independent, right? So we flip a coin with probability 1/4 coming head, and we get this event. And now we say that at least half of these coins come up heads. So in this interpretation of the coins, that means that at least k over 2 of the coins come up heads. And these coins, each coin has probability of heads less than 1/4. Do you understand this transition to coins? Right, so we have this estimators of each block. It's either good or bad. If it's bad, it's head. Okay, they're independent. So it's as if we're flipping these coins and decide which is good and which is bad. And coin comes up head with probability 1/4, and at least k over them are bad. So that means that at least half of the coins come up heads, whether in reality they're biased. So this should not happen. Right? And that's by the example above. This has probability exponentially small, not just small, but exponentially small in the number of coins. Okay, on average, n/4 should come up heads, and we should, k/4, sorry, because of the bias, and reality is half of them come up heads. So that event happens with very, very tiny probability, and the reason, let me scroll it up a little bit, and the reason is this. The reason is the consequence to the Hoeffding's inequality, that we have a biased coin comes up heads, probability 1/4, so the probability of half heads is exponentially small. So we derive this from the Hoeffding's inequality. That's a crucial step. By Hoeffding's inequality. And it's almost time to celebrate, because k was t²/4 right here. K is t²/4, and so we get e to the minus c t²/4. We're done. C is some constant that we don't care about. So we get our Gaussian tail. Good. Median of means. Okay, let's look at the question. If from the chat, if we have Karina is asking, if we have a small data set, is it possible to select k blocks of size m, each, but with random? What does it mean by random repeats? Karina, you can speak up or type. Random repeat of what?
So she means sample with repeats. So kind of, it's possible to select the same value for different blocks.
Oh, yeah. I got it. Yeah. So let's say not the blocks would be the same elements would be repeated with replacement, right? It's like with replacement. So we take x1. It's like we have a bag of these observations, and we pick a random one and pick another, form a block, k of them, then put them back, and then pick another one, and they could repeat. What do you think? Should be okay, right? This argument. It's a good idea, actually. Yeah. No, it should be okay, right? This argument never really relied on this argument didn't really require these blocks to be disjoint. They need to be, we need independent estimators here, but that's okay. If we just pull these numbers at random and then put them back, that's a good idea too. Yeah, you're welcome. That's a great idea.
Doesn't it make blocks dependent from each other?
Because if you second block is basically the same as the first one, because you can get the same values exactly.
In the degenerate scenario, if you have just one value, it will be all the same values. So they're definitely dependent.
Yeah. So we do this with, of course, yeah. If you have one value, you'll always have the same. But okay, something is. So what? Okay, it's there. Yeah, they depend in that sense, unfortunately. That's such a nice idea. I like that. Can it be? Can something be done about it? No. Because it looks, it has the same power. So, okay, so it kills, yeah, it kills the argument, but it feels like it should have the same power. If I just take if I take K bad estimate, K crude estimators, and then take their median, it should improve the robustness of this anyway. Whether I take them with repetition or what, now repetition is a minor issue. Maybe it should be. Oh no, 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 no. No. I'm thinking like, why is it a very surprising result? Is that the random variables themselves, this result is surprising because the random variables themselves, the distribution itself, could be heavy-tailed. It could have tails that don't decay like this. It could have tails that decay very in some other way. We don't only require variance. We don't require any boundedness or something like that. So it should be very random variables like themselves are very spread. And so so if I take, if there is a sample of 1, let's say just n equals 1, whatever estimator I build to this, and in particular this, would be very spread. Right? If I have just one observation, somebody tells, okay, my salary is this. What else can I do? I just have one salary, so I get to assume that this is the mean of this salary is estimator of the mean of the population. There is no other information I have. That's the best estimator then, right? And that salary, maybe it is spread. It doesn't have that required tail e to the t minus t squared over 2. Maybe it just has a variance. So that breaks down. Karina, that was a very good idea. It didn't work, unfortunately. It looks like we really have to have these joint blocks. That what makes it independent, and ultimately the argument depends on it. Yeah, you're right. Yeah, thank you for these comments. It's very useful.
May I ask a question?
Yes, Maxim, go ahead.
So why don't everybody use this? So everyone's using the classical result, right? So when you're asked to estimate the mean, everyone remembers the classical result, and this method is more new to us, I guess. Why no one's using it? So I can see that we need to n be m times k and something. That's a technical problem, but I guess I don't understand why is the classical solution more popular?
Yeah, thank you for the question. One thing is that if we assume that the random variable, that the distribution of the population does not have heavy tails, it has light tails. And that's a pretty natural assumption, like the tails are as fast as the Gaussian one, then the classical estimator has good confidence interval. So this is good. This estimator beats the classical one if you suspect that your distribution could be heavy-tailed, could be kind of a little bit spread, more spread than Gaussian. And that's where it is used. For example, in the degrees of networks, let's say you look at how many people on Twitter like you or something like this, how many people on Instagram, how many friends on Instagram you have, that kind of distribution is actually heavy-tailed. And for that, this method is useful, and I think that people use it. For many other distributions, people assume blindly that the distribution is very light-headed and use that. But I'm not an expert on this. I do not know. Oksana, do you know? Or if you're here, I'm not sure. She's not here. Yeah, I do not know.
So as far as I can see, it seems like the classical solution is just more easy to compute, or I guess because-
Computational, yeah.
because the second one, well, does the classical solution have any advantage except that, I mean, you don't have to care about the n is equal m times k. So if you close your eyes on that, if the classical solution does not have any advantages, then it's strange that people still using this.
Mhm. Okay, let me say that I do not know, but maybe you can check. I'm not, so we care about two things here. One is the kind of the average error, and you can't beat this average error of the classical, this rate of the average error. And the other is how confident are we about this? It's like we're probably, in statistics we say probably approximately correct. Probably here, approximately correct. So as far as the approximation goes, and that is what I do not know, but check. Maybe the classical solution is, there is a factor, a constant factor that I'm missing here. Maybe the classical solution is sharper. So this median of means, maybe the average error is slightly larger, maybe a factor of, I don't know, 1.03 or something like that. I do not know.
Okay. Yeah, but you mentioned that from Kramer-Rao limit, it follows that one is optimal. So the median of means must be worse.
Yeah, the rate, but I don't remember the constant. So it's like this. So any estimator has this bound, but there is this constant that I don't know. So maybe maybe the deal is to improve this constant. So from Kramer-Rao, maybe the classical solution has the best possible constant that I do not know.
Oh,
So
okay, I forgot about the mean error. I was talking mostly about the confidence. So, okay,
the confidence
now I
interval,
get it. Okay,
Mhm.
Thanks.
So that could be the case, but again, up to this little constant error, they're identically the same, except the new one has a better confidence. Yeah. And Karina is asking that for real experiments, all variables are more or less dependent. The same ruler for measuring people's height. I mean, it can be still useful for real. It can still be useful for real data. Dependent. They are dependent, but if you fix the ruler, if you this is kind of a broader discussion about statistics, right? So if you fix the ruler and take the same ruler and go and measure everybody with the same ruler, they're independent. So conditionally on the ruler, on the choice of the ruler, the people's heights are independent. The way I guess there's always dependence somehow, because we can't really sample people from completely independently, but I think it's a pretty good assumption, right? That we choose people independently. There are many survey analysis methods that kind of train people to how do you make polls, opinion polls that are truly, you're selecting people independently. And when you ask, can it still be useful for real data? For example, you mean both of them, right? Because the classical estimator, the mean estimator, this one, it's this one that also relies on the dependence on independence of random. Well, maybe not on the Chebyshev, but it does rely on independence. We always rely on independence. So yeah, it should be useful. That's what people assume. Any other questions? Okay, good. If someone can check what's the mean squared error of this estimators, compare the mean squared error of the classical versus this one, the best one, that'll be interesting for me, because I do not know. And let us know the result. If it's too bad, or it's too good. Good. Okay. We stop recording now.